Hello everyone, and welcome back to my videos on how to cover the P6 topic. In the last video we did ductile fracture. We're now moving on to the brittle fracture. A little bit simpler, this one, and we did go over this in class. Don't worry if you weren't here for that. Obviously I'm going to go through it now so everyone has the same information. We will do fatigue and creep next week. So just to remind everybody, what you need to do is cover the following factors within each of your answers. Okay, so same for brittle fracture: formation, where does it start; propagation, how does it progress; effect of temperature, either hot or cold; and then surface texture. What are the parts like? Usually two, but in brittle fracture we're going to see many parts. Okay, so brittle fracture. You can see here the picture of the window fracturing. So we did talk about this, and we actually broke some pieces of plastic in lesson to demonstrate the effects of brittle fracture. So as opposed to the ductile fracture, brittle fracture is very unpredictable. You'll remember me using the example of the video I saw online of people in China walking on a glass platform round a mountain, and it was designed to simulate a crack, and everyone got pretty scared because they thought it was going to go immediately. So we don't know, and that's why it's called unstable. The material here does not absorb the energy like in ductile fracture. It lets it out, and it lets it out in the form of cracks, so we'll be talking about those. And as I just said, it offers little warning. There's no plastic deformation. The material fractures quickly. This is dangerous. Okay, so to start with the formation, look at the difference. Compared to the ductile fracture, we've now got a compacted and impurity-ridden piece of material. And to demonstrate this, I've only put one air gap in here. This is a very dense material, but the point is being made here. So in terms of the formation, it will form where it can get to areas of weakness, and here is one such area of weakness. So basically these cracks will start where the energy can take hold most efficiently, and it's usually here. It's not going to start, for example, here, because there's no areas of weakness. There's another factor here as well, and well, two. First of all, these lines of atoms here, can you see now, they cannot slide very easily because they're locked up. So each of these is locked up with the impurities here, and because it's so dense they cannot slide, which I've demonstrated here by the smaller movement lines. They can a bit, but not much. So don't forget to mention air, atoms and impurities here. Obviously atoms are very densely packed. The rows are locked together with the impurities, and there aren't many air gaps, but where they are, the force will exploit those areas, as we'll see in a minute. So looking at this now, we did a little task where I said if I was to hit it in a certain place, this simulated bit of brittle material, such as maybe glass or ceramic, where would the crack go? Well, the crack will try and dodge any dense areas, and it will try and head for these weaker areas. So for example, if I was to hit here, it would obviously go for the biggest weak area here, and it may go to the nearest easiest area here, which could be either of these, probably this one, and it will follow these air gaps. Obviously these impurities, which here are green, it's going to go as far away from them as it can because they're locking the structure up. Okay, so I got a member of the class to put a centre punch on a piece of acrylic, which is very much like glass or ceramic, and they hit an origin, and the cracks went out from the origin to the edge of the material. Now, why do they go in these areas? Well, pretty much it propagates in the easiest route. So if you can imagine a river starting at the top of a mountain, the river is not going to go the hard way down the mountain, it's going to pick the easiest routes. And the easiest routes are obviously in the material here are going to be the following the path of the air gaps and dodging the impurities, which on a mountain might be trees or boulders and things like that. So you can see here each of these from an origin, be it this origin over here or this one here, it's going to radiate out in the easiest air gap routes. So you'll remember I said in train windows there's a little hammer that you can use in the event of an emergency. When you hit that window, wherever you hit it, it will crack, and it will crack into thousands of pieces because they've deliberately put quite a bit of air inside that glass. Tiny bubbles, but they put them in there. So that is how it propagates. It propagates to the edge through the easiest route. Do mention the air atoms and impurities here. Okay, so effects of temperature, we will do again 0 degrees, the Arctic, and let's say 50 degrees in a desert area. So what if I hit a piece of material at 50 degrees? Well, obviously the material is expanded in the temperature, not very much, but it has, and what that means is the cracks are able to propagate easier through the material, and that obviously means that it will crack in an easier way, as opposed to cold where it will be harder. So you could say that the cracks will travel easier when it's hot because it's expanded, and the expansion aids the cracking. There's not so much impurity locking in the structure there. It's mostly air which is allowing the cracks to form. So they will travel, I would say, pretty steadily through the material at a hot temperature. At a cold temperature, as you know, the atoms will contract, and that means two things. That means, first of all, it will be harder to get a crack to form, but when the crack does form, it's quite an abrupt crack, and that's because the material has contracted. That means the atoms have contracted, the impurities are locking the structure, and it doesn't want to budge. However, those impurities make a weak point, which, when the pressure is enough, will cause an immediate crack rather than a sort of slow moving crack. And to give you the example here of a windscreen of a car, if you get a crack on the windscreen of your car and a hot day, the sun is shining down on a hot day, the crack can expand, and that is because the heat is expanding the window, and the crack then takes advantage of this, and it moves slowly across the window. Another example in cold would be pouring hot water on a windscreen, which you don't want to do ever. If you've got any crack in your windscreen and it's a cold day, pouring hot water on a window will immediately put stress on it, and the crack will immediately go across the window. So it will happen faster in cold, slower in hot. Okay. Over here we've got the effective temperature as well. We don't really need to use these in this particular case, so do not worry about this. And finally, the surface texture. So students often get a bit confused by this. Glass is sharp, and obviously things which are usually sharp and cut you are rough. That is not the case. As you can see here, there is no roughness. These surfaces here are dead smooth. Okay, the roughness will come from the cracks which form the shape of the actual piece of glass or ceramic. So the surface texture is really smooth, but it's in sharp pieces, which obviously will then have the ability to pierce your skin and hurt you. So be careful when answering this bit here, because all the pieces are going to be very smooth. Roughness is not something that is associated with brittle fractures. Okay, so we've been over brittle fracture, and as before, please lay your answer out in the following way. Be careful with your descriptions here. Please discuss all the things that I've been mentioning in the video, and for brittle fracture you only need to talk about what would happen, the effective temperature in a cold environment. Okay? Right. Thank you very much. See you.